Okay, so we're recording now, and so this is our official start of Big Data. Let me share my screen and then come over here. And we're in the week 12 folder for class today. Again, because let's see, a handful of people in Zoom and pretty light attendance in person, probably will tend to go a little bit faster again than normal. So feel free to just shout out and interrupt me if there's questions at any point. A lot of announcements at the beginning of class today about what sort of the future of the semester is going to look like. So we have about 3 more weeks until 3 more class session weeks, and then it's the end of the semester, so it's pretty close. And so I wanted to give a summary of all of the just graded material that's sort of outstanding that we have left. Just real quick, overview in terms of points. So depending on which assignments you've been required to submit so far, there's been about 250-ish points so far in the class, and we have about that many points, not quite that many, but about that many points left in the semester. Again, the seniors will have 1 fewer assignment than the non-seniors. And so the exact number of points is going to vary depending on whether you're a senior or not. The main thing, final exam. So everyone is going to take the same final exam at the same time. And it will be a take-home exam. In the format, it'll be like a PDF file that you'll complete. So not writing code like the midterm. And you'll get this on Friday, 3 weeks from now, Friday the 29th. You'll have the weekend and that Monday to complete it. And then my promise is, so the grades for seniors are due by Friday. So my commitment is that I'll have those final exams certainly graded by class on this Wednesday, the last Wednesday. And that will give seniors one last chance to review your grades and ask questions about them or get them corrected if there's any mistake. In terms of coding assignments that are left, so before the final, so things that are for everybody, there's 2 assignments left. There's going to be 1 last Twitter assignment for this week, which we'll talk about today, using indexes to make all of our queries super fast. And then we're going to do an assignment on the common crawl data set. So I mentioned this at the very beginning of class, the semester, but this is basically a data set of the whole internet and making a search engine out of that. Ideally, I would have also 2 more assignments in this class, but because it's a little bit crunched here at the end and I don't want to totally overwhelm everybody, there's already going to be a lot of stuff going on, I'm going to not be assigning those 2 assignments. So these are the only 2 sort of for everybody assignments. But then after the final, so the non-seniors only, people not graduating this semester, there'll be 1 more assignment on something called async programming in Python, and we'll see how that can be used to make a lot of the things that we've been talking about in class even more efficient. Also a handful of more written assignments / quizzes. The main purpose of these, again, is to help you do well on the final exam. So this is the 2nd time that I've taught this course. Last time when I taught it, students tended to do really poorly, or at least more poor than I would have liked on this section involving indexes. And so we're going to have a lot of sort of take-home quizzes, practices, sort of things to make sure that that doesn't happen, so that you all are going to do really well on the final exam. So the first of those is passed out in class today, but it's also in this quiz.pdf file right here. And this is just what it looks like. And there's 9 questions about the things that we've talked about so far, and a little bit about what we'll continue talking about this week. This quiz will be due on Monday. So it's, yeah, there's a lot of work for you this week with doing this quiz and the programming assignment. Also, this is called a quiz, but you should feel free to use whatever resources you want. Again, I don't have it listed out here, but fully open Node, open book, open internet, open Postgres, type in whatever you want, and you can even like work with other people in the class. That's all totally okay. There's no restrictions at all on what you can do for this quiz. And then last thing that I really want to make sure that everybody is paying attention to is there are still these 2 also the caveat tasks for your grade. And if you don't, so the special thing about these tasks, I call them caveat tasks because there's no points associated with them. But if you don't complete them, then your grade will just get a 10% drop. So an A grade would go down to a B, a B grade don't go down to a C. And that's a 10% drop for each of these. So if you didn't complete both of them, you'd lose 2 grades. There's 2 of these tasks, the type speed task again, and the culture task. Type speed, working on the Lambda server, playing a game. The culture task, doing some reading and watching videos, and doing a write-up about those. The due dates for these, so for seniors, has to be done before the last Wednesday of the semester to ensure that this is basically as late as it can possibly be, and I'll still be able to get your grades in on time. And so for non-seniors, following that sort of same logic, as late as it can possibly be so that I can still get our grades in on time. You'll have an additional week, non-seniors, that you have until our final exam time slot. Non-seniors, we're not going to use this final exam time slot, but that's just a convenient time to make this assignment due. Any questions about anything admin-wise? What's remaining in class, or what to expect from the last few weeks of class? Okay. Yeah, it will be pretty intense, I think. Quite a bit of stuff to do. So I am really, I think, being very careful about, or being mindful about the fact that I don't want to overload you all with things that are useless or just sort of busy work things, but really making sure that you have assignments that are going to actually be useful for you, not just for this class, but after completing this class and after graduating, moving on to the real world. So it is a lot, but I think it's all going to be things that will be important for you all. So that said, the programming task for this week, our last Twitter assignment. Let's go ahead and take a look at that up here. The idea of all of our previous Twitter assignments was somehow getting the data loaded into Twitter, both correctly the first time and then efficiently the second time. And now that we have correct and efficient data loaded into Twitter, we can focus on making our queries actually fast. And so in this repo here, I'm giving you my solutions to the previous assignments. Then you'll be loading up data in this case. So it'll be the same 10 days of Twitter data that we were using before, but now it's going to be the actual like full days of Twitter data. So not just 10,000 tweets per day, but about 3 million tweets per day. So you have 31 million tweets total that you'll be working with. So there's enough that the indexes will like dramatically improve your query times, but you're not going to have to wait like hours or days to create an index like you would have to if we were doing it over that entire Twitter data set with more than 1,000 different days inside of it. So first thing to do, so preparing the repo and the Docker container. In this case, there's only 2 services that we'll be using. Here in services, there's the denormalized and the normalized batch. So taking away the PG normalized service because that one, inserting data was just too slow in that. And the normalized batch is like effectively the same thing. So only those 2 services. And then getting everything set up is mostly the same as in the previous assignments, with one exception that we're now going to be using this big data folder in your home folder to complete this assignment. So these 10 days worth of Twitter data just by themselves without doing any processing on them is 17 gigabytes of data. And we'll see that after you get all of that loaded into your Postgres database, it's going to be about 100 or so gigabytes of data in your Postgres database. So you won't be able to fit that on your inside of your home folder because you only have 10 gigabyte limits on your home folder in the NVMe drive on the Lambda server. But you have 250 gig limits on the HDD drives where the big data folder is located. So that's what we'll be using. One of the things that's going to come up in this assignment likely is that, so the HDD drives significantly slower than the NVMe drives. And since we are working with just large data sets in general too, even if the drives were fast, it would still be all the commands that you'd be running would be relatively slow. So for this assignment, a lot of the commands you should expect should take maybe anywhere from 10 minutes to an hour just to run an individual command inside of Postgres, assuming nobody else is using the Lambda server at that time. If other people are using it, then if 10 people are using it, then you'll have to split the resources 10 ways. And so you could expect things to take 10 times longer. So this is an assignment that you really don't want to put off to the last minute because it may just be physically impossible to complete it if you wait till the last day or two to get started. One of the things that I think is going to be the most challenging parts of this assignment is working with just this big data volume in general and having our the volumes, the databases stored here. Previously, we've only used what's called the named volume in Postgres to store data, but now we're using this bind mount, and this is going to make things a little bit more complicated in some ways. And I have a big overview in this section right here of why that's complicated. But I'm gonna, in order to illustrate this, I'm gonna switch over to the terminal now and illustrate this a little bit more in detail in the terminal here. So currently I'm in my Twitter Postgres indexes folder. This is the location of the assignment. I'm going to change my directory though into the big data folder here. And right now I have these 3 folders inside of here. Created, the Flask web is from one of the very first assignments in this class, and this PG denormalized and PG normalized batch from this particular assignment here. One of the things we've seen before, CD dash will take you to whatever the previous folder that you were inside of the shell. And so that's a convenient way to switch back and forth between these 2 things. I want to real quick open up this docker compose.yaml file and highlight here lines 8 and 20. These are the bind mounts located in the docker compose file. You won't have to modify these at all. You shouldn't modify these at all. You will have to modify the ports like before, but you won't have to modify the mounts. You won't have to modify the volumes. But you also notice there's no, so right now I'm at the very end of the file, I press Shift G, there's no volumes section at the bottom like we had before. So Postgres is not, or sorry, so Docker is not managing any of these volumes for us. We have to do it manually. And the big downside of having to do this manually, so now I've changed my folder back into big data, ls-l. So you can see over here, this column of the ls-l normally tells us the user ID or the user account that owns a particular folder or a particular file. And so Flask Web, my user test account, that's who I'm currently logged in as, owns this Flask Web. And so I could CD into that just fine and modify, do whatever I wanted inside of here. But I don't actually own these PG denormalized or PG normalized batch folders. And so if I tried to do CD into PG denormalized like this, I'm going to get a permission denied error because user test does not own these folders, and only the owner has permissions over here to work with these folders. This user ID right here is technically something called a user namespace inside of Linux. This is like a user ID that is a sub-user ID of my current logged in user ID. That's my user ID as my current account. And so it is possible to modify these directly, but it's really, really awkward to do, and we're not going to go over how to do it. The main thing that you're going to need to know how to do, though, for this assignment is what if, like, so we've seen before in the previous assignments that you're loading in data, and at some point maybe something goes wrong and you need to sort of reset your assignment, delete it all, and start over from scratch. How do you do that? And in this case, we can't just do rm, say -rf, pg, denormalize, something like this. That's not going to work because we don't have permissions to do that. And so in order to actually do this, you have to do it from inside of the Docker container. Because inside of the Docker container, we will have permissions. These user IDs right here actually correspond to the root user inside the Docker container. And so when we're inside of the Docker container, these will be our user IDs, and so we'll be able to do these modifications. Yeah, so this is just what we've seen so far. In particular, previously, we were using this Docker volume prune in order to delete volumes, reset things. Can't do that. We'll be having to use these commands that look something like this in order to reset the Docker containers. I'm going to run these commands here in a second just so that we can see what it looks like. But before I do that, let's Docker compose pg normalized batch, not batch, psql like this. Oops. Docker compose exec. I want to go into psql here and just dig around inside of this normalized batch container for a second to see what things are like. First thing I'll do right now is, let's see, I don't think I've actually done this command before in class, but \timing on, usually when I'm working in psql, this is one of the first things I do. What it does is it just, every time I run a command, it'll tell me how long that command actually took to run. So here, \d again gives us our overview of all of the contents of the database. So there's all of those things right there. And if I did something like select count star from tweets, so counting the total number of tweets, we can see that this is taking a fairly long time because there's just quite a lot of stuff in the database. Again, 31 million or so tweets inside there. And so this command takes like, I don't know, 30 seconds to a minute or so to run. As it's doing that, let's switch back over here. When you're loading the data, again, it'll be this load tweets parallel.sh command. I've already run that for us in these Docker containers. But I've included the output of these commands, this command right here, so that you can get a sense of what the output, your output might look like. And in particular, how long it might take to do this loading tweets. So for PG denormalized, here's the runtimes down here. There we go, almost 20 minutes or so to load the denormalized data set. Again, this is when there's nobody else using the Lambda server. And then for PG normalized batch, the output's quite a bit longer, so I've just added these ellipses here to, I don't know, there's a couple thousand lines or so. But the important thing is this output down here, just shy of an hour or so to load this. So in total, you should expect, like, first time you run this, at least an hour and a half or so to just get the data set loaded. Come back over here. Okay, so now it's done this select count star, and it took 22 seconds just to do this right here. So this just verifies real quick that we have some data in the database. And now I'm going to go through the process of resetting the database, deleting what's in there, because again, we can't use that Docker volume prune in order to do this. So in order to do this resetting, I'm going to go inside of bash instead of inside of psql. And we talked about before that there's this PG data folder that contains all of the information in your database. So that's right here. Let's do it real quick, just see like how much disk space this folder is actually using up. So disk use -hd0 $PG data like this. So 25 gigabytes for this folder. That's just the normalized version of this database. And this is before I've created any indexes or anything on this data set. So this is just after having loaded the data. And if I've made a mistake loading this data, or I want to reset my database for some reason, what I have to do is when I'm inside of Docker Compose like this, inside of the image, I will run the rm-rf command, $PG data. So I'm gonna wait a second here before hitting enter. But again, this PG data, the location that the data is stored in, rm-rf, deleting the contents of a folder. And I'm currently the root user inside of this container. So I have access now to delete this piece of information. And when I do that, it's going to delete it from that big data folder inside of my user account on the Lambda server. So this command right here is how I'm going to actually free up disk space if I need to free up disk space. Do that, there's a lot of things to delete, so it takes a minute or so to delete it. Eventually you get an error message that looks like this, saying that it's trying to delete the very last one of these folders, but it can't do that because Postgres is currently running. Rerunning this disk use command though, we see that it did in fact delete everything except for this, just this data folder right here. If I were to run psql again, then it'll crash because we've just deleted everything. But if I do docker compose down, and then docker compose up -d, so I'm in my the master branch right here, and the master branch again has the ports set to be 1 and 3 down here for these services. I don't have permissions to load things onto those ports. So real quick, check out my solution branch, check out solution. Those have proper ports set over here. So when I do the docker compose up, it'll actually work. Docker compose up -d. And because when this service comes up, it'll see that the database PG data folder is empty. Whenever that folder is empty or that folder doesn't exist, that's when it's going to rerun that schema.sql file to recreate the database. So now if I come back up here to my psql command going in the PG normalized batch, this is the service that I deleted things from before. We saw before, after I deleted things, when I tried to re-enter the service, it crashed because it was in an inconsistent state. There was nothing, no files in our database cluster. Again, the database cluster is the Postgres' term for the actual service running on an individual database. But now that it's brought the service down back up, Postgres reinitialized itself, run /d, we can see that these tables have been recreated from the schema. And now if we do something like select count star from tweets like this, nothing in that folder right there. And if we open up bash instead of psql and do something like disk usage shd not $pg data like this, there's not a lot of stuff in there, but a little bit of stuff corresponding to just the schema definitions for that particular folder or for that particular database. And now if I wanted to reload the data, I could run the load tweets parallel.sh again, and it would reload that data for me. So this is a long explanation of that. Instead of running docker volume prune like we were doing before to reset your data or to delete, free up space, now you have to do this longer system of actually going inside of the Docker container and deleting it from within the Docker container. That's the easiest way for you to get the permissions to delete these files and free up the space in your big data folder. Any questions about doing that? Okay. Yeah, again, I think for the most part, the concrete stuff of like the tasks that you're supposed to do in this assignment will be relatively straightforward. But if you get stuck on something like this could be a major stumbling block for you, and something that you're not going to be able to, or that's going to be difficult to figure out if you're not familiar, if you're not looking out for it. But if you do get stuck, these one-line commands right here combine everything that we just talked about into deleting the stuff from the those particular volumes. So that's loading the data. Talking about that. So quick aside on the disk usage. So we saw that the disk usage for the normalized batch was 25 gigabytes. For the denormalized, actually, if you look at the disk usage, it's about 3 times higher, 75 gigabytes. So the reason for that, we've talked about a little bit, but the denormalized just stores a lot of redundant data. So it stores, so part of this is the redundant data that's being stored. It's also just the JSON-B data type that's used to store this is not the most efficient storage-wise, because it needs to, we haven't talked about the internal formatting of that, and we're not going to, but it has a little bit of overhead to make things more efficient. So the normalized, we've seen so far that it's faster, but it also uses a lot less data. But the downside is that it's just more work programming-wise. The denormalized, really straightforward, really easy to use programming-wise. If we compare this, so these are the 10 files right here that are we're loading from the main data set. If we compare this, the disk usage up here to the actual disk usage of the original data set 17 gigabytes. So even our normalized one has maybe 50% overhead or so. And the reason for that is all that overhead that we've talked about in Postgres, with the overhead for all the tuples and the overhead for all the pages, and the fact that pages are going to necessarily have some amount of empty space inside of them when you can't fully fill it up with rows, and so on. So that's overall, actually, that's probably about as efficient as you can ever hope to be in a database, is like a 50% overhead over the raw files. It's a pretty good ratio. And again, so the advantage, disadvantage of storing things in the database uses a lot more disk space, but the advantage, you'll be able to get your queries down to millisecond times instead of having to use these MapReduce procedures, which take hours to days. Okay, so then the second step, creating indexes on the normalized database. So starting with the normalized database, there's inside of the assignment right here, ls, there's this folder SQL.normalized_batch, and there's 5 There's 5 different SQL queries inside of here. And your job, you don't have to change, you're not allowed to change anything about these SQL queries, but you're supposed to create some indexes for those SQL queries that make them run fast. Originally, with no queries, it takes about 2 minutes to run these 5 queries. With no indexes, it takes 2 minutes to run these 5 queries. And after you create your indexes, my solution ends up taking about 3 seconds. And the vast majority of these 3 seconds is just the overhead of bash and its timing. If you were to type in the queries themselves directly into pSQL, you'd see each query is actually just milliseconds. So in order to create these queries, or in order to create these indexes, that'll require thinking about all the stuff that we were talking about last week and making sure that you're using index-only scans when possible. And let's see, if we come over to actually look at some of these. Normalized batch 01.SQL. So a relatively straightforward query right here. Just putting a, make sure you have an index on the tweet tag so that you can do an index scan on here. But then if we look at some of the more complicated ones, like number 5 over here, now you have a really complicated query over here, and you have to think in detail about what's going on. Okay, there's a join here. I wanted to use a merge join. In order to use a merge join, what indexes do I have to have on tweets and tweet tags based on the column that's over here? I see there's a group by, so I have to think about how can I make it use an aggregate group by instead of the hash aggregate. And there's a limit. How do I effectively take advantage of these limit clauses? In order to do this, there's going to be a lot of different possible ways to create indexes on these tables that will work, be correct, give you fast results. My solution, though, creates 3 B-tree indexes and 1 of what's called a GIN index. So this is something that the GIN index is something that we'll talk about this week. Probably not getting to it today, but definitely by Wednesday. But for the most part, except for this last one right here, you should be able to, at this point, have enough knowledge to complete these first problems. It's important over here that these say pass. If this says pass, that means you've loaded the data in correctly. If these are not passing, then you're getting incorrect results from your SQL queries, which means that you've probably not loaded the data correctly somehow. So you need to go through that process of deleting the contents of your volume and reinitializing your database, reloading the data until you get these to pass. Last part of this assignment is on the denormalized database. And if we come up here, you'll see that I have the SQL.normalizedBatch folder already included for you, but I do not have a SQL.denormalized folder. So I'm not providing you with the appropriate queries to use on the denormalized database. So for the denormalized database, you will not only have to create indexes, but you will also have to create the queries that correspond to these queries in the normalized database. As we talk about the GIN index this week, we'll also talk a little bit more about creating queries for denormalized databases. All the queries that we did for the Pagilla assignments, it was always for the normalized database. We haven't talked about using that JSON-B data type and actually writing queries for it. So this third part of the assignment will have you actually writing those queries, getting practice using the JSON-B type, and also doing indexes at the same time on that. So this third part here. We haven't yet seen the material for doing this, but we'll complete that by Wednesday this week. One of the main things, though, to note or to remember for this denormalized one, you know you've written the queries correctly because you'll get passes on these statements up here. If you're not passing these queries, then it doesn't even make sense to think about the indexes. If you're not having correct SQL queries, then it doesn't matter whether they're fast or not. But Notice how much slower the denormalized database is with queries without indices. That the normalized database was about 2 minutes or so. So it's slow, but still maybe something that we might be willing to wait for. But the denormalized database, even way, way slower, 40 minutes just to run these queries right here. But once we create the indexes, so this is with the indices, we get the same, like down to seconds runtime. And again, the queries themselves are just milliseconds, and this is all due to overhead of Bash and the testing scripts. In terms of submission for this assignment, so no GitHub actions for this assignment, no test cases like that you're required to pass. The reason for that is this assignment just uses too much disk space and computation for GitHub actions. So every time you push, you can't be uploading 100 gigabytes of data to GitHub. GitHub will get very mad at you if you do that. Or at least with their free tier of GitHub, they'll get mad at you. If you were paying them, then they would be happy to just suck money out of your credit card. But in general, when you have these like large data sets, there really are no good techniques for doing these benchmarking or testing programs automatically. Really what people do in practice is they would test on small data sets like we did in the first versions of these assignments, and benchmark on these small data sets, and then basically just trust that things are going to generalize to these larger data sets. Trusting the tests, the accuracy of data sets is not too much of a stretch of the imagination. It's pretty easy to generalize like correctness tests from small data sets to big data sets. But generalizing benchmarks from small data sets to big data sets is a really, really tricky thing to do, and something that's like a CTO of an organization or whoever's in charge of performance at an organization is that's sort of what they're being paid for is their knowledge of how to efficiently do those tests. And that just takes a lot of experience. We're not going to be covering that in detail in this class. Instead, we'll just be working on the large data set in general. And so basically like this was a production system. To submit your assignment, so a couple of steps. So first of all, running these commands down here, these commands will time all of your SQL queries for both databases and store the results in these files over here. You'll add these files to your GitHub repo, and then I will look at them in order to do the grading to check out how fast your times were. What the output, what the contents of those files will look at like is just something like this. And I'll be looking at these, in particular the real runtime down here, to make sure that your queries are actually fast. When doing the grading, so 30 points on this assignment. For the normalized queries, runtime is 10 points. You saw that my queries took about 3 seconds to run. You have 5 seconds allocated to you that you are allowed to use. And every second you use beyond those 5 seconds, you lose 2 points out of the 10 points for this part. So you can go up to 10 seconds. But if you're any slower than 10 seconds, then you'll get a 0 on this part right here. For the denormalized, you have 10 points that's for the correctness of the denormalized queries, and then again 10 points for the runtime, and same sort of grading criteria that you have 5 seconds to use, and then every second beyond that is a 2-point penalty. But additionally, for the denormalized, since it doesn't make any sense for your denormalized queries to think about the runtime if they're not correct already, you must get full credit on the correctness in order to get any credit on the runtime down here. When you, oh yes, one last thing about this assignment that I didn't mention above, as you're creating indexes, in general, the good practice when working with a database is you never want to directly type database commands into pSQL that modify your schema. So if we're inside pSQL like this, in general, it's bad practice to do create index, whatever you're going to type. Instead, what is good practice is to put this command into a file, put that file into your version control so that you always can recreate your database schema from version control exactly. And then once it's in the version control, run that file in pSQL. And so in order to help you get into these good practices, I'm asking you to put whatever indexes you do create into a file called schema-indexes.sql in the appropriate service directory. And that'll ensure that if you did bring the database down and brought it back up, Postgres would automatically create these indexes for you and create your schema to include the new indexes. And so things would stay fast. You would not have to manually remember that those indexes were created and recreate them manually. That'll do that automatically. But yeah, so you upload all of these things, commit them all to your Git repo, upload them all to GitHub, submit the repo to Sakai, and I will look at these files in order to do the actual grading. One last hint. So for the indexes that I created, some of them took up to 30 minutes to create. Some of them were fast, took only a minute or so to create. Some of them took up to 30 minutes to create. And again, I was doing that when the Lambda server was under no load. Nobody else was using it to do these things. But if 10 students are running a create index command at the same time, then this 30 minutes will become 300 minutes. And so you should potentially anticipate that each command, one of these create index commands that you run, could potentially create 5 hours or so to, or take 5 hours or so to run. So because they take a long time, you don't want to just be blindly creating whatever indexes you think you might need. You want to sit down, think about it a little bit more carefully about what you might need, and then only create the indexes that are likely to be useful for you. Any questions about anything related to this assignment? Yeah, here.
All right, is there any way to like do like you said the process like the background?
Oh yeah, good question. The question is there any way to make the things go into the background? And anytime you're working with Docker, the background processes are a little bit weird. But the easiest way to make something go into the background is to not run pSQL through Docker Compose, but run pSQL directly from the Lambda server. And we saw how to do that 2 assignments ago, the very first Twitter Postgres assignment, where we did something like pSQL and then Postgres : / whatever the URL right here is for your particular database that you're connecting to. So I'll just type URL here for short. And then if you put the create index commands into a particular file, then you can use the file redirection, so the less than right here, and then it's going on to the next line. So the less than for input redirection, then the name of the file. So it'd be something like services, pg normalized bash, schema-indexes.sql. And this will run pSQL on the Lambda server, sending whatever commands are in this file into Postgres right here, creating the index. And then here I could use the ampersand to send it to the background, or the no hub command to prevent this from disconnecting if my service is disconnected. Yeah, it's a little bit awkward to do. I've done, so yeah, in the past, I've done this for index creation tasks that I expect to take an extremely long time, like more than a day or multiple days, or long enough that I know I'm gonna have to close the lid of my laptop and move to a different Wi-Fi connection somewhere. So I would recommend only doing this if you think you're actually planning on disconnecting your internet from the Lambda server for whatever reason. And at least the way that I went through this assignment is actually just in Docker compose exec pg normalized bash psql like this, running things inside of psql using the explain command very heavily with those 5 SQL queries to see what is the current plan for them, and then identify, okay, here's a seek scan that I want to get rid of, or here's a hash join that I want to convert into a merge join, and then construct an index trying to make that particular part of the query faster. And usually I'll just type the index creation command directly into pSQL here. And then after I do that, copy and paste it into the file that I'm putting into my GitHub repo, like this right here. Yeah, finding a good workflow or there's lots of different possible workflows for doing this. You can use whatever is going to be convenient and work for you. Did that answer your question? Good question. Any other questions about this assignment at all? Okay. So then in terms of material for this week, we mentioned before that there's a lot of different index types in Postgres, and all we've seen so far is the B tree. So we're done talking about the B tree. We've talked everything that we need to talk about that, but we're going to talk about those other index types now. This week in particular, we'll be looking at something called the hash, the gin, and the rum indexes, and how they support what's called full text search and the JSON search. And so the JSON search will be useful for us when we're doing the denormalized database, and the full text search. Some of the queries in the normalized database, the very last one, query number 5, is actually searching the contents of the text of tweets rather than some of the meta information. So that's a full text search, and we'll need a new technique besides the B tree in order to do that. Okay, so first of all, the hash index. And again, referencing this Russian haber.com website in order to talk about the hash index. So what we talked about before, the B tree index is sort of equivalent to the binary search tree from data structures, and the hash index along that same metaphor is like a hash table from data structures. So whereas the trees give us logarithmic worst case runtimes, hash tables give us constant runtimes, but that's not worst case anymore. It's technically this amortized average case. But it's also exactly what Python dictionaries use. They use hash tables for their implementations. This O of 1 time compared to log n, again, in my opinion, there's you should think of these things as the same thing. They're not from a theoretical perspective, but again, when you take the log of 10 to the 15, that's only 15, basically like constant, super small. And especially when we're talking about the B trees with their huge fan out factors, the log base B of n was like at most 4 or 5. So very, very little performance boost from using a hash index. So because of that, they're used very, very rarely. If you're only ever doing equality searches though, they will use fewer page accesses, so they can be faster for that. But equality search is the only thing they're good for. We saw the B tree is used good for range search, sorting, lots of other things. Hash index only for equality search. It does not sort the results. One of the Postgres specific limitations is that, like with a B tree, when you delete items, the B tree will go smaller. The hash table will never grow smaller. you cannot use an index-only scan in a hash index. You can only use the bitmap scan or the index scan. You can't use multi-column indexes. And if you're on an older version of Postgres, there's even more limitations. So because of all these limitations, people very rarely use these hash indexes. Runtimes, though. So again, K, the number of items that we're actually retrieving from our select statement. The number of table pages accessed, the same as a B tree. When we're doing an index scan or a bitmap index scan, the B tree supports the index-only scan. So this would be 0 page accesses and an index-only scan. The index pages accessed of K divided by B. Similar, but to the B tree, again, here the B tree has this extra log B of in factor, but this is a super, super small amount. Another thing that we haven't talked about yet is something called buffer cache optimization. And this is something that makes B trees even more attractive relative to a hash index. What a cache optimization is that so far, when we've been talking about page accesses, we've been assuming that the Postgres actually touches the disk every time and reads things from disk. But individual pages that are read very often will be stored in memory, so you don't have to re-access them from disk. And this makes lookups much, much faster because you avoid these disk accesses. Internally, it makes insert, update, delete more complicated to keep up with the ACID guarantees, but we don't have to worry about that. There's this famous joke that you probably heard before, but there are 2 hard problems in computer science: cache invalidation, naming things, and off by 1 hour errors. This cache invalidation refers to this particular optimization right here of keeping the commonly used pages in a B tree in memory. So again, not going to talk about this in detail, other than it's good for you to be aware of it. There's lots of references on this. This reference in particular, though, you do not need to, you're not going to be responsible for anything related to the buffer cache optimization on the final exam. But this reference, things related to the hash tables and all the other references we've talked about so far, you are responsible for the final exam. Anytime you're creating a different index type, what the syntax for that looks like is this is the part that is new in the syntax. So you still have the on table name. Previously, we just had straight into the column list, but now you can say using and then the name of a particular index type, and it will create a hash index in this case instead of a B tree index. If you omit the using clause, then it's equivalent to having using B tree, because B tree is the default index. Any questions about the hash index? Main things to make sure you know are these 2 points right here and the used for and the limitations down here. Okay, then what we're going to move into next is for full text search and how our indexes interact with full text search. So what full text search is when we're using this like operator in Postgres with a command similar to this, this is an example of full text search. This is where we're looking for the word corona anywhere inside of the text field of the tweets. So the text field stores the actual tweet itself with the message that somebody is sending. And so if that contains the word corona anywhere, then we would get the ID for that tweet. So this would get us all the tweets that somehow talk about coronavirus, or Corona the beer, or Corona the city. Not trying to do any sort of differentiation on the topic that way, just literally has this string somewhere inside of it. So recall that the percent operator in the like clause is like the glob, the star in the shell can be matched with anything. So that's why this looks for this word inside of this particular table right here. But importantly, with the way this query is currently written like this, none of the index types that we've talked about so far, neither the B tree nor the hash index can speed up this query. So we're going to first talk about a variation of this query that can be sped up using the B tree and why that will speed it up, why the B tree can speed it up. Then we'll see why the B tree can't speed up full text search in general, and we'll talk about some of the alternative indexes that can speed it up and how they work. So if we imagine instead of having 2% signs like this, we have only a single percent sign at the end of the query like this, then this is something that can be sped up with a B tree index. The reason is because this query right here is equivalent to this query right here, that we can replace this percent operator with a range search with a greater than or a less than, like this. So anything greater than or equal to corona and anything less than corona B. And just by the way ASCII-betical ordering works, this will be equivalent to this up here. And we saw before that the B tree supports these sort of range operations. The examples that we saw before were for integers, but anything that's ordered, you can do the range operations. So strings work just fine too. And so the B tree would do this just fine. One question though is, what if we replace the like with the I like operator in the above query? So instead of where text like corona, where text I like corona. And the I like, the I stands for insensitive. So I like is case insensitive. So if we do this command right here, instead of this, this is equivalent to all of these different conditions plus more put together. So we're not just doing the range for the lowercase c, but we're doing the range for the uppercase C and then uppercase O right here, and all the different possible combinations of uppercase characters. And so it turns out there's like n squared different combinations like this of uppercase and lowercasing everything. And so even though the B tree could do each one of these individual lines efficiently, it can't do all n squared of them efficiently. And so the I like operator cannot be efficiently sped up, even though the like operator can. There are some databases, so SQLite most prominently, that default to using case insensitive search for like operator. But for this reason right here, this performance reason, Postgres has this distinction between like and I like, so that if you really, that you only get this non-performant code if you actually explicitly ask for it. If you use the like operator, then you'll get the performant version that can be sped up with a B tree. This is an important sort of concept to understand, that these like operators can be sped up with a B tree. And the way that it'll come up in your assignment is that if you have, let's say we're searching for hashtags, and we want any hashtag that is somehow related to coronavirus. So something that looked like this, hashtag Corona star. So this would be match Corona, coronavirus, and any different variation of that. Then this is something that you would want to create a B tree for to speed up this query right here. Any questions about that section, using the B trees to speed up the percent queries, the like queries? Yes.
I'm just curious, like, why can't they just make the hidden mechanism of like itself and B trees, but it's just not?
What do you mean the hidden mechanism?
Like if using a B tree is not really using like, why can't I just use B tree?
Oh, the question is why can't the like query just automatically use a B tree? And the answer is that it will automatically use a B tree. So this here and this here are equivalent to each other, but you don't have to write out this thing in order to use the B tree. That if you have the B tree that can speed up this query, Postgres will use that B tree to speed up this query. So you should feel you should feel free to use the like operator, and you'll still get the performance benefits of it. You don't have to manually do these things, this expansion, but this is just the way to understand why a B tree can speed this up. Does that answer your question? Yeah, good question. Any other questions about this section? Okay, then we're going to move into full text search, commonly abbreviated FTS. And we'll start by talking about full text search outside of Postgres. There are a number of popular full text search engines available out there, and we'll want to understand Postgres's limitations and compared to the other systems, and how those other systems with their limitations are compared to Postgres. But the way to think about full text search is it's basically what like Google and Bing are doing, and only inside the database, not through the web engine, but directly in SQL. So the first thing to note is that there is no SQL standard for full text search, and there has been like attempts to propose different SQL standards for full text search, but because it's still sort of an ongoing research problem how to do optimal full text search, they're not willing to standardize it at this point. So people have been working on full text search in Postgres for 20 years now. Still has not made it into the SQL standard. Whereas in comparison, we talked about how the JSON was just recently added into Postgres starting in 2014, sort of to compete with MongoDB. And we have a good understanding of how to do SQL queries on those now. So that has been added to the SQL standard. And but eventually, probably there will be a standard SQL standard for full text search, but at this point there is not. So most full text search systems are not SQL based at this point. They're NoSQL systems. So that means there's none of these ACID transaction guarantees that we're getting with Postgres. The most popular system currently is called Elasticsearch. And it's a pretty powerful full text search engine, but again, it can't be combined with SQL, and it has its own custom syntax. So I've never met a single person who liked the syntax for Elasticsearch. It's, I don't know, maybe you don't like SQL syntax either, but I think it's much, much nicer than Elasticsearch, and especially because it's easy to generalize. Like once you learn it, there's so many different problems you can solve with it. But like the Elasticsearch syntax, there's only one place you can use that. So it's always hard for me to remember what things are, and I always have to just copy and paste from Stack Overflow. Major disadvantage of using any of these, like, so if you're Reddit or Instagram or just a service, whatever company you are, you have a web page, you already have Postgres or some other database storing your actual main data in it. Major disadvantage of adding one of these full text search engines is that you have to like actually add a whole nother service. So Docker doesn't make that too hard now. That just means another Docker container. But somehow you still have to configure that Docker container's like Elasticsearch engine, making that talk to your Postgres database somehow or transfer the data into the Elasticsearch engine. So it's not at all simple or trivial to do. Let's see, so people have automated ways of integrating Postgres with these other systems. I've tried using them all. I've never gotten any of them to work. I know there are companies that use them in production, so they must work, but I've never successfully gotten them to work. So it's a big pain in the butt just to add an extra service just for this one functionality. Another major limitation of Elasticsearch in particular is that it used to be open source, but it no longer is. And this touches on a big debate in sort of the open source world right now, the last maybe 5 years or so, and how open source is interacting with cloud providers. So Elasticsearch used to be licensed under the Apache 2 license. So Apache is a license, or Apache is a product, a web server, one of the original open source projects. The Apache license, kind of similar to like MIT style license compared to a GPL license, pretty, very few restrictions. And the way Elastic, the company, made their money was they offered their own Elasticsearch cloud solution. So they had their own sort of competitor to AWS. Actually, I think they were running on top of AWS for a while. But if you wanted to use Elasticsearch and you didn't want to go through the hassle of running your own servers, you would just hire Elastic to run the servers for you, and that's how they made their money. And they made a lot of money that way. So it was a $2 billion market cap company as of a couple of years ago. And they've been growing continuously since then, still not on the decline. But because they were Apache 2, very liberal license, Amazon started offering their own Elasticsearch. There was nothing in the license term, so that prevented them from just offering their own service to compete with Elasticsearch's hosted service. They call it OpenSearch instead of Elasticsearch on Amazon, but it's just literally an Elasticsearch engine under AWS. And so Elastic, the company, relicensed their Elasticsearch library as what's called the SSPL license. It's not an open source license. One of the criteria of an open source license is that there are no restrictions on what you can do with the software. But the SSPL license, the restriction is that if you're a cloud provider like Amazon, you're not allowed to run Elasticsearch. You're not allowed to sell it as a service. MongoDB pioneered this strategy, so MongoDB also not open source anymore. And a lot of formerly open source products that have this model of making their money through services are going this way of using the SSPL license, not being open source anymore, but preventing companies from sort of monetizing their products. So in response, Amazon just forked Elasticsearch and they're continuing developing off of the open source one. It's been about a year since this happened. My sense is that Amazon has been very successful with this strategy, made a lot of money. Elasticsearch, though, still continuing to be very successful. People, if you already have products on Amazon, people tend to pick Amazon. If you don't have products on Amazon, people tend to pick Elasticsearch just because, or pick Elastic's hosting company just because they have a little bit more expertise, a little bit cheaper product. Other competitors, so Lucene Solar, they are open source libraries, similar to Elastic, came before, no longer as popular. Elasticsearch actually built on top of these products. They're internally used by Elastic. So some people use these directly if you're like embedding it into a project, but most people still just use Elasticsearch. My favorite alternative to Postgres is called Grunga. This is an embedded full text search engine. So it's a library that you can just like import into any sort of project. It's very easy to include in other projects. For people who've used C before, it's just a single C file that you add to your project, and now you have full text search. If you're using Python or something like that, it's just again pip install one thing away. And the reason that I like Grunga over these other ones is it has good Asian language support. Grunga supports a lot more languages than these other products up here. And this is something we'll talk a little bit about here. Maybe next week we'll get to it, about how do you support these different Asian languages and like exactly under the hood what's going on with all these different products. Grunga can also be embedded into Postgres with an extension called pgrunga. It is pretty easy to do, but you lose the ACID guarantees if you do this. So advantages of Postgres: you can use the full SQL capabilities. In particular joins, you can have your data still be normalized. You don't have to store everything in a denormalized fashion. Postgres also, the full text search, generally considered superior to the other actual SQL databases, RDBMSs, things with ACID guarantees. So like MySQL, SQL Server, Oracle, SQLite. Disadvantages though, this main one up here. So we've talked before about storing tables and indexes separately. If really all you care is you have text that you want to be searched and there's no metadata associated with it, then you're basically storing that text twice, once in the table, once in the index. So that's twice the disk space that you're using compared to, say, Elasticsearch. Elastic only stores the index, doesn't store the table at all. That makes things slower. There's active development about this. Actually, we're currently on Postgres 14 and it did not land, so maybe in 15 this will be fixed and you can have a table without it, or an index without a table, but right now you can't do that. The big disadvantage, though, there's not a whole lot of ranking algorithms supported. So one of the things that basically, Google is so much more popular than Bing, basically because Google is much better at ranking queries than Bing is about finding things that are relevant. And that's where most of the ongoing research in full text search is going, as how do you rank queries better? And Postgres does not have good support for that right now. And it's a really hard problem. So maybe 20, 30 years from now, Postgres will get state-of-the-art sort of ranking support, but it's not in the near future. That said, so Postgres didn't used to support the JSON-B type. So Mongo, Cassandra, all those other NoSQL solutions were developed around this need, but then Postgres added the JSON type, and now it's people say Postgres is better at being Mongo than MongoDB is because it still has this JSON support and all the ACID guarantees. And at some point, something similar will happen to full text search in Postgres. If I were starting a new company, I would still just rely on Postgres and let these researchers develop things out rather than making my internal tech stack much more complicated, adding all these other products into it. Lots of references about full text search in Postgres. We'll be getting details of these starting next class, and how to actually do the full text search in Postgres. That's going to lead us into a discussion of the new index types, the GIN index and the RUM index, and doing the queries that you need for the Twitter assignments. So yeah, next class we'll have all of that finished up, and you'll have everything that you need to complete the Twitter assignments. The quiz that got passed out again too, quiz.pdf, that has some full text queries on it as well. So probably like 80% of that quiz you're able to do right now, but then after Wednesday's class, you'll be able to do the rest of it as well. I think that's a good stopping point for us for today. Any questions about anything? Question is, when is the quiz due? It is due on Monday. Oh, so 1 week from today. Yeah. And again, you're allowed to use any resources you want for that, including working with other students, running things in Postgres, looking at whatever you want on the internet. Good question. Any other questions? Okay, then hope you all have a good rest of your day, and see you on Wednesday. Where did my Zoom go?